as people are coming in, so I'll invite Igor.
Should I use this?
Yeah, if you use this, or if you feel more comfortable, you can use that.
Yeah, some of you have heard this question already, so I apologize for the repetition. But since I kind of kept asking this couple of questions, various people, and I never got the answer, so I thought, why not I present them here. So one question is about how much you can geometrize topology. So if you start with a manifold, say if M is an aspherical manifold, take the universal covering. So if you think about negatively curved manifold, say, the universal covering would have unique geodesics. So the universal covering would look like this. So for any 2 points, there is a choice of geodesic. Right. So it's a uniquely geodesic space, and moreover, this is equivariant. So you have 2 points, A and B, in the universal cover. If you move this, the geodesic goes to geodesic. This gives you this gives you a bicoming. So for any pair of points, there is a canonical choice of geodesic. But it has this additional property that if you have chosen 2 other points, say, then the intersection of 2 such would be like empty or a point. If you generalize this situation from a negatively curved manifold to, say, cat -1 manifold. So it's a manifold topologically, which has cat -1 structure, invariant under the group. So gamma is pi1 of n. In that case, you might have the situation when two geodesics intersect maybe like this. The intersection is convex. The intersection of 2 geodesics is a convex subset of an interval. The question is, can you actually do this picture for any aspherical manifold? Purely topologically. So does there exist a gamma invariant convex bicoming? So it's kind of a way to navigate. It's a navigation system, if you like. You are in this universal covering. Sorry? Yeah, convex means the following. So if you have quadruple of points like A, B, A prime, B prime. If you connect, I want a choice, so what is a bicoming? For any pair of points, you have a choice of path between those 2 points. So you take the path connecting A to B, and you take the path connecting A prime to B prime. You require that the intersection of these 2 paths is an interval, possibly empty. So whenever 2 paths meet each other, they should continue along, and maybe then diverge. There is no metric. It's a purely. Not really, yeah. It's just kind of a way to get from one point to the other, but in a consistent way. So it's a purely topological statement, but of course it's kind of topological analogy of this geometric picture. Yeah. I want it to be continuous, yeah. So this bicoming is a function from m hat, m tilde to the space of paths.
So this is supposed to imply that word problem for gamma is solvable?
A word problem for gamma is solvable. I don't know. There is no geometry really. I mean, those paths don't have to fellow travel or anything. Yeah, I'm not sure. I don't know if it's...
I mean, there's examples where the probability... It's not... You don't have to have a solvable word problem for the fundamental.
Probably you don't. I don't see any reason why this would imply. There is no geometry here. I mean, it's a kind of a topological statement, really.
So why do you ask for convex intersection and no single point intersection?
That would be a stronger statement, but even if you do convex, that would be already a step towards the single point. So some kind of navigation system. The question is, I mean, can you construct it for any aspherical manifold? This should imply, of course, that it's aspherical, right? It's you should be able to find it. Of the manifold. No, I don't know. I mean, it's a uniqueness of geodesics property, pretty much, right? If you have the uniqueness of geodesics, you can probably make this. But assuming you have no geometry. So that's the first one.
Martin, what's your definition of semi-hyperbolic?
Well, it's like, no, but that's what I was asking, because then, yes, so there should be some uniform bounds, so a few points. You've got points which are distance less than k apart, and the choice of paths have to stay f of k or not.
Yeah, here there is no geometry, really. I mean, there is no...
You can make this topological quickly, you know.
It's a question of geometrizing topology. I mean, whatever you want.
What are the consequences if the answer is yes?
It would hopefully lead to some geometry of manifolds in general, you know. It's good to have negative curvature of a manifold, right? Then it generalizes. You want to have cat minus 1 curvature, cat minus 1 inequality. And this is something weaker than that. So the question is, does it cover all possible situations or not? I don't know. Yeah. So should we go to the second? I have the second one too. So yeah, it should be true. I mean, it's whenever you have uniqueness of geodesics, that should hold. What?
Even dimension 3. What about the tall Bangalore with the software?
Yeah, I don't know, but it should, in dimension 3 it should be true.
Well, that's easy. So you just treat them as a cover like a product, and you just go by it and transfer to it.
Okay.
Just take the thing and strip them by it. Or we put the line and go by it. Go ahead. So, yeah, so, yeah, effects. So for solid, it's good. Well, for ill potent boost, you just take it straight. Polycyclic. Because you're not requiring any geometry, they're not really close to geodesics. That's what the limits.
Yeah, okay, so should I continue? Yeah, okay, the second question is, again, it's about metric spaces. You try to construct some kind of geodesic metric space, and you want to do it. It's a relation between this geodesic flow and the, say, negatively curved manifold. So if M is let's start with the negatively curved manifold. So is a closed negatively curved manifold. Then you take this geodesic flow on the space, right? So think of of T1. Again, you take the universal cover. So, and then think of T1 of this universal cover as a union of lines, right? As a union, as the union of orbits, of our orbits, of the flow. So from the point of view of like rough geometry, this is quasi-isometric. So T1 of M is quasi-isometric to the original manifold M. Right? There is a quasi-isometry. There is this projection map. And then, but this is a union of lines, right, of geodesic segments, like infinite lines. It's a metric space which is a union of lines. Those are straight lines. And this is, when you project, you just, if you have a couple of lines here, you identify a couple of points here, right? If they happen to belong to the fiber, then you identify them. The question is, what if you forget about this M now? Suppose you started with an object like this. Can you reconstruct the original manifold in an equivariant way? So it's a kind of a rough question. It's not really precise, but so can one reconstruct M tilde from? So you want to be a manifold, say, from T1 of M, which is a union of straight lines. So if I try to make this more precise, maybe you could say, suppose you started with a metric space, which is a union of lines, and each line is geodesic in this metric space. The metric space itself doesn't have to be geodesic, but each line is geodesic, minimizing, globally minimizing. And assume, say, that this space, let's see, this space, say, is quasi-isometric to some, say, hyperbolic group. So metric space consisting of lines. X is quasi-isometric to a hyperbolic group. For example, the fundamental group of this manifold. Then can you describe a procedure that would tell you which point to identify on the lines to get the manifold back? So how to identify points to obtain a manifold. Yeah, I guess I should, if I want a manifold, I probably should assume that this hyperbolic group is a like fundamental group of a manifold, a negatively curved manifold.
Could you remind us of the status of this question of two manifolds with negative curvature with the same fundamental group of homomorphic? Is it still open? Or?
I don't know. It's still open for me, at least. I don't know.
Because that would solve that. This is a question from Raman. If you take two manifolds of negative curvature with the same fundamental group, it's quite easy to see that their real tangent bundles are canonically homomorphic. The question is to go from this homomorphism
Yeah.
from the real tangent bundles to homomorphism of the non-real manifolds. A few years ago it was still open, maybe it's not open today. I don't know. Do you know the status of
Well,
this?
I think it's true as long as each is four cores, which
This is true.
four is true and which is fine.
And this is true by some sophisticated technique, not because there is no some canonical machinery to
That I
make
know.
this. This is not the way we suggest it. So this is true. This is your thing?
The thing is not enough to get a constructive proof of this from the model.
It would be very nice.
Yeah, outside the realm of local symmetric spaces. Any more comments? Questions? Any more questions you may have? So anybody else? Martin? Perhaps we want balance.
That's okay.
Now, I've deliberately chosen them to be embarrassingly simple questions that I can't answer. Okay, so, well, first of all, for questions about mapping class groups and out of FN, there's some nice sources for this. Actually, I should ask Aladdin. On your webpage, do you have a list of? Oh, AIM. Yes, sorry. Yeah. Okay. So on the American Institute of Math webpage, linked from Aladdin's webpage, there's a very expansive problem list about lots of problems of geometrical theory. So particularly young people looking for problems, it's a very good place to start because the problems are often written with background explaining why they're interesting, so they don't just seem like arbitrary questions. Okay? And another place is a book whose title I can't remember. It's got questions about the mapping class group or something. So the editor is Farrell, anyway. So questions about mapping class groups. That's not exactly the title, so it's something like that. Maybe it's mapping class groups and related topics. And this is a sequence of essays by various people. Okay, there's one by Aladdin, this one by myself and Karen Vogtman, where people sort of write little expository essays about aspects of these groups and then deliberately give a list of questions. Okay, so that's a very good place for questions. And I want to just take one question because it's a question that really bothers me. It keeps me awake at night. It's very irritating. It's very easily stated. And I'll explain to you why I care about this question. So there's this analogy between mapping class groups, out of FN, and SLNZ, or higher rank lattices in general. But you might say, see here, if you pass to a subgroup of finite index, then you still got a lattice. So it still enjoys all the properties of the lattice. In particular, it enjoys all the rigidity properties of the lattice. Okay, so if I take a subgroup of finite index here, n is always equals 3. If I take a subgroup of finite index here, then I said it obtains rigidity. So there's a baby form of that, okay? So that we still have things like all quotients or all normal subgroups. All normal subgroups are well, so kind of trivial things you have to exclude, finite and central, or with finite index. Okay, so you don't have any interesting infinite quotients. Now over here, as we saw, that's too much rigidity to expect, but still you want some aspects of rigidity here. So it certainly should at least be true that if I take the say the homology, the first homology, if I just veganize these groups, then those groups should at least be finite. And that's true. Yeah, that's not very hard to prove. And one kind of trivial way to prove it is that these groups are generated by elements of finite order. Okay, so they're finitely generated groups, they're generated by finitely many elements of infinite order, so you veganize them, you get a finite group. But that's kind of cheating. Okay, that's not really telling you much about the group. Now the trouble is that some lesser level of cheating enters lots of the proofs of rigidity type theorems for these groups. Okay, so lots of rigidity type theorems for these groups, mapping class groups out of FN, at some point appeal to the torsion in the group. And that always feels like cheating because these groups have torsion-free subgroups of finite index. Okay? So take a torsion-free subgroup of finite index, and you'd like to be able to continue to prove rigidity theorem. So the warm-up question, which of course is the embarrassing question I can't answer, is if you take a finite index subgroup of a mapping class group, in here the genus should be at least 3, always. Or about Fn, then it is the ionization finite. Can't even answer that. So let me. And this question keeps coming up somehow every time you want to prove some rigidity type theorem and extend it to subgroups of finite index. So let me say some of the theorems you'd like to prove. So here are some of the things you'd like to prove. So for example, if you take, so always I'm taking, let me just stick out of Fn. Take a finite index subgroup of out of Fn, and you might ask, so does every map to say to out of Fn with m less than n. So if rigidity, if you got some sort of super rigidity, then all such maps should have finite image. So does every map have finite image? Okay, so know how to prove that if gamma is the whole of out of Fn, but I don't know how to prove it if gamma is a subgroup finite index. Okay, there should be other things like does every, actually I'm really not sure what the answer to this one should be. Does every map from gamma to a mapping class group have finite image? I really don't know, actually. Are there any interesting ways in which the automorphism of a free group can act on the surface? Okay, or its subgroups of finite index? Okay, now there's lots of other things I could state like this, where the conclusion should be images of maps have finite image. Okay, but you've got no chance of this being true if your group maps onto Z. Okay, so this is really step 0 in anything you would like to prove about rigidity for these subgroups, and I'm just completely stuck at step 0.
So step 0, did you check it on a computer for some examples?
Yeah, and I believe so.
You can schematically.
Yeah. The trouble is the number of...
This is
Yeah.
something that can be checkable with
Yeah, people have tried this. Yeah.
Okay, so this has been checked on many examples.
Well, I think the trouble is that the numbers get very big very quickly, right? So what can you do? So for example, in the mapping class group, you might... Well, there's obvious subgroups to try. You might map to SLNZ. Yeah, you might map to SLNZ, reduce modulo your favorite prime, and take the kernel of that map. That would be a torsion-free subgroup, and trying to Beanize that. And of course, a computer, as you say, you can check this. But
anyway, I'm happy
So-
to learn that this
Okay.
has been checked.
okay,
So your conjecture is sometimes true.
yeah, the conjecture is sometimes true. I should point out, so there's lurking behind this. You see, so this seems like a very naive question. I mean, somehow that's why I like it. Right? So it's very naive, so it's irritating, but it's related to lots of things. You see, it's a question of do out of Fn and mapping class groups have Kaufman's property T? Now, Anderson has a proof for mapping class groups. So some people, I'm told there's a bit of a gap in, but it's anyway. There's available proof that mapping class groups do have T. But you see, if a group has property T, the expected answer is no. The expected answer is that these groups do not have T. Right? But if a group has a subgroup of finite index that maps onto Z, then it does not have T. Okay, so this is one way. You actually did succeed in finding subgroup finite index that maps onto Z, and I don't believe they exist, but if they did, then that would be a way of proving these groups don't have T. Now, just one other worrying point about this is that not everything works as well as you hope. Okay, so I mentioned the other day a theorem that there do not exist non-trivial homomorphisms from out of Fn to homeomorphisms of, say, Rd with D less than that. So out of Fn refuses to act below its natural dimension. And so you might hope that that extends to subgroups of finite index, for example. That's the sort of thing you'd like to do. But it doesn't. Okay, and actually, the question here turns out to be not exactly this, but if D is less than n minus 1, then is every map, or you can just ask this already for the representation theory, just for linear maps, is every map finite? Now, why do I have to go down to n minus 1? And this is a slightly worrying point in all of this. But you see, you might start asking this question for n equals 3. In fact, I did. But actually, for n equals 3, there's an answer. Okay, and so the real question here is for n greater than or equal to 4, and that's because for n equals 3, there is a subgroup of finite index that maps onto Z. Okay, so let me tell you what that is, because it's kind of an interesting construction. So, take a free group of rank 3. There it is. Okay, then, so this generates your ABC. Take the following index 2 subgroup. So take the index 2 subgroup. Well, index 2 subgroup corresponds to a two-sheeted cover, right? So let's say I take the kernel of the map to Z mod 2 that sends A to a generator and kills B and C. Okay, so you get this two-sheeted covering. With Galois group Z mod 2, let me call the Galois transformation tau. Okay, so that's actually the level of pi 1, that's just conjugation by A. Okay, now so inside out of Fn, this looks like you have to do it for out of Fn, but believe me, it's okay for out of Fn. I take the subgroup of out of Fn, this finite index subgroup, that preserves this index 2 subgroup up to conjugacy and will commute with this Galois automorphism. Okay? So in particular, it will act on homology of this graph here. Okay, so it'll be a math, and you can actually check it's onto the automorphisms of the. It just acts on the homology of this graph. But I'm taking the subgroup that commutes with tau. Okay, so this is rank 5, but tau will split h1 of x up into a +1 eigenspace and a -1 eigenspace. It's an involution. Now this has got dimension 5. So one of these has dimension 3, that's that one, and one of these has dimension 2. Okay, now this subgroup is preserving that splitting because it commutes with tau, which means you get an induced map from this gamma onto GL of this -1 eigenspace, which is GL2. So this means out of F3, it's not obvious it's on 2, but it's not so hard to see. You just take a Nielsen transformation, one of these handle slides, they generate the image. So actually, out of F3 has a subgroup of finite index which maps onto GL2Z. So if I go into a subgroup of index 6, following that back, you get a subgroup of finite index out of F3 which maps onto a free group of rank 2. Okay? And so this question, actually, you can get into the mod by going to subgroup of finite index for n equals 3, but the guess, the reason to think that that's special to n equals 3. And for n equals 4, such groups don't exist. And if I drew the same pictures, so that here n was 3, if I drew the same pictures starting with n instead of 3, then what I'd actually end up with is a subgroup of finite index out of Fn that maps onto SL n-1 of Z. Okay. And then you should still get rigidity because you're only mapping onto SL3 and not SL2. Okay, I was going to ask another question, but that one went on longer than I thought. So there's only this one little question, but it's an obstruction to a lot of nice mathematics. Actually, can I just take 1 minute to say the other question? So I don't have time to explain why the other question is so interesting. This is a completely unrelated question, but it's so easy to state. It's one of those things that you think, when somebody tells you, you think, I'll do that on the way home. And then you waste evening after evening on the bus on the way home trying to do it. And you have to have one of those problems that you do on the bus, or fail to do on the bus. Depends how long your bus ride is. Okay? So, because as everyone knows, if you take a hyperbolic 3-manifold, conjecturally 5 is over the circle. Virtually 5 is over the circle. It has some subgroup finite index that maps onto 5 is over the circle. So pi 1 has a subgroup finite index that maps onto Z, just like this. But you might also reasonably conjecture that actually if you've got a hyperbolic 3-manifold, then there actually exists a subgroup finite index in pi 1 that maps onto a free group rank 2. Okay, that property is called largeness, having a subgroup finite index that maps onto F2. Okay. Now, if you map onto F2, then by passing to subgroups of finite index in F2, okay, and pulling them back, you get a sequence of subgroups of finite index in gamma where the rank of the first homology is going to infinity. Okay, so this, if you're large, that implies that sometimes called infinite B1, so the sup of the rank of the first homology of gamma naught, so few coefficients with gamma naught of finite index in your group, but that's infinite. Okay, so infinite virtual B1. Okay. Okay, so now here's a stupid question. So this is an obvious implication. Okay, that's an obvious implication. So there's not a single example known, but surely they must exist. So construct, let me make it a challenge. There's no way this can be true. So a challenge is to construct any finitely presented group. Okay, so I'm going to use a different lectic, it's got nothing to do with geometry now. Construct any finitely presented group gamma so that this virtual B1 is infinite, but the group is not large. Okay, so there should be other reasons. So if you're large, then you make this first homology have an arbitrarily large rank by going to subgroups of finite index. That shouldn't be the only reason why you can make this B1 go to infinity. But there's not a single example known. Now it's important that you have finitely presented here. Okay, it's easy to write down classes of finitely generated examples, so I'll just give you one. So if you take gamma Z with Z, okay, so that means you have an infinite connected sum of Z's, and then the other Z acts by just moving them along. That's finitely generated, but not finitely presented. Well, it's easy to see that one has you can make the abelianization as big as you like by just taking inside here this so keep the connected sum, but just pass to that subgroup of finite index, you just get a certain chunk, you abelianize that, and it's got rank m, or m plus 1. Okay, so it's easy to make the rank of the first homology get as big as you like by going to subgroups of finite index. But that's not a finitely presented group. And an interesting exercise is to prove that if you take any finitely presented group which maps onto that one, then it is large. Okay, and this seems to keep happening. Okay, so it's not so hard to dream up different classes of finitely generated groups that have this infinite but are not large. Okay? But then, in every case, it seems to be that if you only take a finite number of the relations, that is, you take a finitely presented group mapping onto that given group, they all turn out to be large. Okay? So I don't for a minute believe that these conditions are equivalent, but it doesn't seem to be so easy to construct an example. Comments?
Do you have any questions? Thank you.
So I have a question about polyhedron. And I have a question in projective geometry. So the question is to find a polyhedron in the projective space, Pn. First, you may think of it. So Pn is the projective space of Rn plus 1. And so this polyhedron has faces, n minus 1 dimensional faces, and I want to have symmetries with respect to these faces, but not Euclidean symmetries or hyperbolic symmetries if it were in Hn, including Pn. So I want to have a projective symmetries with respect to each faces. Fi. And so for each of the face, n-1 dimensional face, I want to have a symmetry. And there is a theorem of Weinberg which tells you that if these symmetries satisfy some compatibility condition around these codimension 2 faces, then if you look at the group generated by these symmetries, it will be a discrete group. So this group gamma is a group generated by these symmetries. And so for Fi, all the n-1 dimensional faces. And this Weinberg theorem tells you that so under compatibility condition around the two-dimensional, the two codimensional faces, and these compatibility conditions are just that if you look at the dihedral group generated by sigma I and sigma j, and the image of P by this dihedral group. This dihedral group has to be finite, and it makes a tiling around these faces. And this Weinberg theorem says under this compatibility condition, then the union of the gamma P, for gamma in gamma, will be a convex set. And if you add some conditions that for each vertices, the corresponding Coxeter group is a finite Coxeter group, then in fact this convex set will be open. And so this convex open set sometimes is the whole of Rn. For instance, if you start with the square and you take the Euclidean symmetries, so you can do this kind of construction in any dimension. But the question I'm asking is, can you have such a construction for which you don't have a tiling of all? What you tile is some properly convex set, and but n is arbitrarily large. Such a group with n arbitrarily large and omega properly convex, meaning its closure is bounded in some affine chart. No. So for sure. So most of the known examples, the group gamma is Gromov hyperbolic. So according to Kiewicz, and you have limit in dimension when gamma is Gromov hyperbolic. But there are examples in dimension 3, 4, 5. Of such construction where gamma is not Gromov hyperbolic. And I don't.
The requirement is that the on each face, at each vertex is, at each zero-dimensional vertex is finite.
Yes, that's the condition for that I want, so that I will be sure that this compact polyhedron will be in the interior of the convex set it tiles.
Right, so Vinberg has this criterion for,
Hyperbolic. Yeah.
for you have some, whatever, this Cartan matrix or something. I mean, you start with a polytope, you write down a Coxeter group, and then the question is whether you can
No, the theorem
realize that in the same dimension as the polytope.
No, the theorem
No, I
is
think
the
it's
same
more
as this
like-
one, except that this is hyperbolic geometry instead of projective geometry.
It's more like whether you can realize a Davis complex. When this Davis complex is a manifold, whether you can realize it in some open set.
Minimal dimension.
Yeah. This kind of.
No, he didn't even say hyperbolic.
No, that's the point. If it's hyperbolic, the answer is for sure there is some limit on the dimension.
Whether you can get this Vinberg representation in dimension n, where n is the dimension of the polytope. Right? That's what I meant by open. No, your representation into GLN, GLN plus 1, and the polytope is dimension n. That's the question. That's what the key point was.
Key point is that maybe if you want in terms of Coxeter group, okay, I start with the Coxeter group. I want a representation of this Coxeter group, such that all the generators of the Coxeter group are symmetries with respect to the faces of this. Thank you.
Questions? Anybody else? Anyone else? Questions? Peter? Any questions?
An argument of Lafont shows that if G is a word hyperbolic group, and assume G is residually finite, I suppose at this time conceivably a vacuous condition, though nobody believes that. And then G has a subgroup H of finite index which is a unique product group. So remember what a unique product group is. It means if A and B are finite, non-empty, subsets of G, of, well, I think I should say of H, then there exists the unique A in A and B in B such that AB is the only way you can write that. So such that AB equals A1, B1 with implies A equals A1 and B equals B1. In fact, Delsont's argument even shows that H is a two unique product group, which is so. So if you get finite non-empty subsets of H, then you can consider all products A, B with A and B, and there's one of those elements which can be only written in that way. And there exists, oh no, not unique, there exists, I'm sorry, I shouldn't want that exists, I don't want that, I'm sorry. There exists such as A, B. Is that better? In fact, Delsont's argument even shows that H is a two unique product group, though. An argument by Strognowski many years ago showed that a unique product group is uniquely two unique product group. So we know that also a left orderable group is a unique product group On the other hand, we don't know the reverse converse. Converse is open. It's elementary that left orderable groups are unique product groups. So, I mean, it seems ridiculous that all unique product groups are left orderable, but that's yet to get a counterexample. So, what I'm really interested in, can Delsont's argument be used to show, well, the groups over there, the word, to show word hyperbolic groups. So you're going to have to assume residually finite. Have a left orderable Oops. Subgroup of finite index. So a good starting point, maybe that seems rather overwhelmingly difficult, so let's try something a little bit easier.
Just so does that mean, kind of specific, I mean, you took a fundamental group of a hyperbolic manifold,
Yeah.
then the question would be, is there a subgroup of finite index that's,
Left orderable, yeah.
that's not known.
I think that's unknown.
So this is a much more general question.
Yes. So I mean, this is going to be, so the first, so, I mean, so Dalson's argument, you're looking at, of course, he's looking at the action of G on the Cayley graph. Even bioorderable, but there are many ways to do this, but so my question is, can one see of the free group of rank 2, let's call that F2, F2. So can one see that can one see that F2 is left orderable by looking at its action on the Cayley tree. The Cayley tree. I suppose you could say yes, but then you won't tell me the argument. So, this is interesting. I mean, another open question is whether there exist non-trivial left-orderable groups with property T. Of course, we know that there are word hyperbolic groups which have non-trivial word hyperbolic groups which have property T. So, if one could carry this out, one could find a left-orderable, non-trivial left-orderable group with property T.
I guess if there are no questions, maybe we will just close the session.
Yeah, thank you. Thanks everyone for the cooperation. Yeah.